Okay, sorry about that, guys. I didn't catch my phone in time and it did die. So, all right, so I'm not sure if you guys got this last part, but the big difference between molecular orbital theory, which is used to predict whether a bond will form between two atoms, and valence electron theory is just going to talk about where those high concentration of electrons are going to be in the bonds, right? Okay. So let's see. And just remember with molecular orbital theory that it's almost going to replace those orbitals with totally new orbitals whenever a molecule does form, whenever these bonds do happen. Okay. And the unpaired electrons in each of those are going to be dispersed. And we'll look at that in orbital hybridization. Okay. So let's see. So 8.2, let's look at this one real quick. So we're gonna look at this in class a little bit more, but molecular geometry, it's fine, it's kind of fun. Basically what I want you guys to realize is that there is a charged repulsion, and that charged repulsion, right? So like if I have magnets, the two negative sides are going to repulse. They're going to want to get away from each other, right? And then the opposite ends are going to attract, right? So the charged repulsion of these molecules, of these newly formed molecules, are going to determine the shape of the molecule and how it's held together by these covalent bonds. Okay. Remember that in the valence electron theory, it talks about those high density regions along the axis. Those are going to have a very strong negative repulsion, right? So it's going to push away some of those other, some of the other bonds, right? So let's take a peek at this. Real quick, the tetrahedral, right? So this one thing to remember is it has 4 regions of electrons, okay? 4 regions of electrons. And where are those 4 regions? So let's say we've got our central atom, and then we've got our other atoms. Okay, so our 4 regions are going to be these bonds right here, right? Those are going to be the high regions where those electrons are going to be more condensed. Okay, so whenever they talk about 4 regions, they're talking about, in this case, it's going to be 4 of those bonds. Okay, so the angles that you're going to have with the tetrahedral are going to be approximately 109.5 degrees. Okay, because these cannot get any further away from each other without becoming closer to another, right? So if you think about the negative here, 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 and here, they're pushing each other away from each other the best that they can to the maximum place where they can, and that angle for each of those is 109.5 degrees. Okay, let's see here. So the next one is a trigonal. I think that's how you pronounce it. Trigonal. So this also has 4 regions of electron densities, right? And 3 bonded pairs and 1 unbonded, right? Pair, 1 unbonded pair, I should say. All right, this unbonded pair here actually has a stronger repulsion force. And so therefore it's got a, here, let me show you real quick. So let's say we've got our central atom here, and then we've got 3 bonded pairs, right? So we've got 1 here, 1 here, and then 1 here. Right? And then if you think about it, it's got, let me use a different color here. It's got these 2 unbonded, right? It's got 4 regions of electrons, 1, 2, 3, 4, and it's got these 3 bonded pair and this 1 unbonded pair. This 1 unbonded pair has a stronger repulsion force. So it's gonna push these bonds then actually a little closer together. Okay, so this is gonna have a pretty strong force. It's gonna push these 3 a little bit closer together. And they're also though going to still have about 109.5 degree angle. Okay, so that's your trigonal. Let's see here. The next one is trigonal planar. All right, and it has 3 regions of electron densities, right? It's going to have a double bond, one double bond, sorry about that guys, it looks kind of sloppy there, and then it's going to have 2 single bonds. Okay, so this one, as it says, it's going to be in the shape of a plane, and then just remember tri kind of means Y. Okay, it's gonna make a Y shape. Okay, so you're gonna have your central atom, and then you're going to have, a double, a single, and a single. Okay, so 3 regions of electrons. These do not have to all be the same atoms outside here, okay? I'm showing them the same color, but it doesn't have to be all the same atoms, okay? So this right here is going to be in the shape of a Y, and it's going to be, it's going to have an angle of 120 degrees. Okay, and it's going to be on a single plane, right? So those angles are going to be at about 120 degrees. All right, the next one is a bent. The bent one. So this one has 4, let's see here. So it's got 4 regions of electron densities, right? And it's got 2 of those are single bonds, and 2 of those are unbonded. Okay, 2 of those are unbonded pairs. So it says that these angles can technically be 104.5 degrees or 109 degrees or 120. I think it gave the exact degree of water, because water is one of the typical bent ones, but I can't recall what that was. But anyway, so this one will look like this. You've got your central atom, and then you've got, right, you've got your 4 regions of electrons. You've got one here along this bonded axis, one there along that bonded axis, and then you've got these 2 unpaired, right? 2 single bonds and then 2 unpaired pairs, okay? And it says this angle right here is the one that they're measuring, okay? So that is the angle that they're measuring. That can be 104.5, 109, or 120. To be quite, oh, I'm sorry, it says here 104.5 was water. So this one right here is water. I don't think that's on a test, but if it is. So the confusing thing, here's the thing that got me a little bit too, was that the unbonded pair in this trigonal had a stronger force. So it pushed those angles a little bit closer together, right? So I'm wondering why, and I haven't researched this yet, why these unbonded pairs don't produce a pretty strong force as well, and make this angle almost less than a 90 degree, you know? So, because here that unbonded pair forced those angles to be closer. And here we've got two unbonded, so you'd think that that would be a little bit closer. So anyways, that kind of caught me off guard whenever I was reading it, and I've not researched why that, that is the case. So anyway, so those are that's that, okay? All right, so guys, for class on Monday, assuming we have class, why don't you guys, let's see, we'll talk about orbital hybridization, okay? And then we'll finish up this chapter. It's kind of a short chapter. To be honest with you, it's not my favorite chapter. I don't know why. There's just some confusing things in it that it's just not super fun. So let's see here. The homework that I would like for you guys to do. So again, Monday we're gonna look through a lot of this stuff. We're gonna do some little hands-on activities. So 8.2, I would love for you guys to do number 2, all of number 3, number 4, number 6, 7, and 8. Okay, I'll send that out in an email. But do numbers 2, 3, 4, 6, 7, and 8. And we will talk about polarity and orbital hybridization in class. So, and then that's it. So just do that for Monday, guys, and then we'll go from there. All right, you guys have a fantastic weekend. See you later.